folks, and welcome back to the Infodump, the series where I do a deep but not necessarily scholarly dive into a particular topic. We are, of course, continuing with physics, which I forgot to mention at the start of the last doubleheader, but I think last part of this double feature, whatever. You fucking know what I mean. And, you know, as I was about to say, I think people got what I meant. I fucking hope. Anyway, I have stepped away, had a little bit of a drink, had a little bit of a think, had a little bit of a research, had a little bit of a write. It is now 1 a.m, and I have decided that this episode is going to be on... Well, this is going to be sort of stepping out of the subatomic realm and into the atomic realm. We are still very much dealing with microscopic things here, but they are more macroscopic, closer to macroscopic, less microscopic. Microscopic instead of nanoscopic, let's go with that. Or picoscopic, or however the fuck you want to think about it. Anyway, the first thing to know when we step up from the pre- or subatomic stage to the atomic stage is, well, sort of the contents of that step. Because it's not just that we're stepping from subatomic to atomic, we are stepping from fundamental particles to atomic, because there's not really much between there. The only thing that we are stepping over, really, is the nucleons, the composite particles that make up the nuclei of atoms. Now, I touched before on how those are made up of 3 quarks. Now, what I didn't touch on is what they are beyond that. So if you've taken a chemistry class and you remember much from it, then you probably know the basics, at the very least, of what protons and neutrons are. But from a physics perspective, let's just go into it real quick. Protons are nucleons, which is to say particles comprising an atomic nucleus, with a mass of 1 atomic mass unit, which is defined as the mass of a proton or a neutron, and a positive charge equal and opposite to that of an electron. Now, neutrons are defined as a subatomic particle, a nucleon, that has a mass of 1 atomic mass unit and has no charge. Obviously, they are also defined by what flavors of quarks comprise them. In the case of a proton, that is 1 down and 2 ups. In the case of a neutron, it is 1 up and 2 down, so they're basically opposites. Despite that, they have, very much different properties. It's not like they are completely inverse, they are still very much similar. But, there you go. Now, here's the thing. Just like if you take 2 magnets and put the north ends or the south ends together, they'll push each other away. Same thing happens with protons. They have the same electromagnetic charge, and so they push each other away. Neutrons, via the strong interaction, keep the atom's nucleus together. Now, the neutrons themselves are definitely not force carriers or anything like that for the strong force. They are instead just sort of the coincidental glue that it happens to use. Or more accurately, they are more like the anchor point that it's binding the protons to. The thing being, though, because they are also finicky and made up of quarks and whatnot, too many neutrons also causes an atom's nucleus to split apart. the reason that elements with very high numbers of protons are so unstable and so radioactive is because there eventually comes a point where a whole neutron is enough to be the difference between too little and too much. And when you're dealing with that big of an amount of stuff in a nucleus, even a slight tip in either direction can cause a catastrophic chain reaction. Now, that's not to say that it's only very high-numbered atoms that are radioactive or volatile. The fact is, eventually, every atom more complicated than deuterium, which is hydrogen with a single proton and a single neutron, every atom more complicated than that will eventually decay into either protium, which is a proton or just a proton, so a hydrogen with no neutrons in it, or a deuterium, which is hydrogen with a proton and a neutron. That is the final state that when entropy takes hold, all matter, all atoms will essentially regress to. More complicated atoms do exist and do have ridiculously, sometimes even impossibly long lifespans. You can have a nearly perfectly stable atom of most elements, not all, but most, such that it will take ages to decay. Quite possibly longer than the universe has left. In which case, yeah, since we're not, going the absolute infinite time route, it probably won't decay back to either protium or deuterium, but that's because it's been eaten by a black hole. Or something like that. In which case, it's been spaghettified down to its fundamental particles. It really doesn't matter what shape those fundamental particles were taking in their instance before spaghettification. Now, here's the thing. Those different amounts of protons and neutrons are what we call isotopes. And when it comes to nuclear physics, specifically radiation physics and the like, dealing with plutonium, uranium, cesium, that sort of thing, that's what's really important, is what isotope you're working with. Not what, the number of electrons relative to protons is. Not its, its ionization state. What's important is the number of neutrons relative to the number of protons. The isotope. And again, that is something that scales very chaotically and messily. We, at least as far as I'm aware, do not have a predictive function exactly for what the safest number of neutrons to have in an atom of a particular number of protons will be. We just know there are sweet spots, and the further you are away from those sweet spots, the messier it gets. So of course, if you have all protons, if you've only got the one proton, it's fine. You can't make it work with anything more than that, though. And the more protons you try to cram together, the more explosive the end result will be, because of course you're trying to cram more things that don't want to be together, together. And yeah, if you've ever tried stuffing way more than should fit into a container, you probably can imagine the sort of explosive results I'm talking about. As soon as there is no longer enough pressure to hold everything in place, boom, it shatters. And when it shatters, oh boy. Now you have to deal with rogue protons flying at near the speed of light, which is a regular part of radioactive decay. And that is not fun, because it means that now everything is getting, hit with ionizing radiation. Specifically, alpha particles. Yeah. You don't want to have to deal with those. They're the least dangerous in terms of the types of ionizing radiation, but that's only because you can put up a sheet of paper to stop them. If you're actually fucking exposed to them directly, you will end up with skin cancer after a couple minutes. Depending on quantity. And I'm imagining an atom of uranium, which is number 92. So that is 92 protons, all exploding at once per atom. Yeah, that's fucking bad for you, Chief. But, japes and humor aside, we should probably start by defining a couple terms real quick. I mentioned way earlier about atomic mass units. Those are defined as the weight of a proton or a neutron. That's all there is to it. It is the simplest way of measuring atomic weights. Now you might be wondering where electrons fit into that scale, and the answer is they kinda don't, because they're so fucking light, you usually just rounding error them out and it's fine. Essentially, one electron weighs about roughly a 2,000th of an atomic mass unit. And don't worry, elements only go up to the 100 teens, definitely not beyond 2,000, so unless you have, a god super ion, you will not have enough electrons in your atom to add a significant amount of weight. And even if you manage that, the mass of the atom is the least of your fucking worries, my guy. So yeah, you might be wondering why we don't measure things in, atomic mass units. Well, I mean, if you live in America, the answer is because freedom units! Yeah! But if you live in a place that uses an actually sensible measuring system, the metric scale, the answer is because, as it turns out, the metric system isn't all that sensible, really. It is based on hard, objective things, which is good. Everything is made to be compatible and convertible into other forms of units that are within the metric system, so you can, say, okay, 1 gram is the amount that 1 cubic centimeter of water weighs. That's good, that's helpful. But then you realize that depending on where you are on the globe, gravity is different, because it's not a perfect sphere, it's an oblong spheroid. So, yeah. The reason, at its core, why we don't use atomic mass units or other easily, objective, verified numbers is because they're fucking big. Yes, I know, 1 atomic mass unit is very small, but that's sort of my point. So, there is a constant called Avogadro's number that is used to convert atomic mass units into grams and vice versa. Essentially, it is how many atomic mass units you need to have a gram. It's a very fucking big number. I'm gonna pause for a second so you can guess what it is. You done? Good. It's about 6.02, and a little bit more, but we're rounding, times 10 to the 23rd. If you're not familiar with high-level math, or, well, high school level math, really. Essentially what that means is 602 followed by 21 more zeros. Or if you want to be more precise with it, 6022-14076 followed by 15 zeros. Yeah, that is big. If you want to be doing all of your calculations in the form of, what would that be? Let's see. Well, 10 to the third is thousands, 6 is millions, 9 is billions, 12 is trillions, 15 is quadrillions, 18 is quintillions, 21 is sextillions. So unless you want to be doing all of your weight calculations... Oops, sorry, bumped my mic. Unless you want to be doing all of your weight calculations in the form of, hundreds of sextillions... And yes, sextillion is a bit of a funny word, but hundreds of sextillions... No thanks. I don't think anyone wants to have to write times 10 to the 23rd after, like, let's say you're reading a recipe, right, and it says, 54 times 10 to the 23rd AMUs of sugar. That's a lot worse, really, than just 9 grams of sugar. Just 9 grams. That's all. But, of course, it's complicated. Because this is also where we have to get into the difference between weight and mass. See, as I mentioned, gravity is different depending on where you are on the globe. And obviously, gravity is hugely different depending on whether you're on the fucking globe at all. If you're up in the International Space Station, the best you can ask for is pseudogravity from rotation. If you're on the moon, you've got 1/6 of Earth's gravity. If you're on Mars, you've got about 1/3. If you're on Venus, you're pretty damn close, but still about, I think it's roughly 1/10 or so off. Or if you're on Jupiter, you're fucking weighed down by the weight of your skin, essentially. Forget all the other organs, just your skin alone is cripplingly heavy. Yeah, obviously measurements of weight are going to vary greatly depending on what gravity strength you're in. So, when it comes to actually measuring the weight of something, you kinda don't want to be relying on atomic mass units, because you're measuring weight, not mass. We usually, in terms of the numbers, treat them as interchangeable when we're talking about stuff here on Earth, but it's important to remember that that's only because that's what we've calibrated all of the instruments and the equations for. When we say something with a mass of 10 kilograms, we mean a mass that in Earth's gravity at, the place where they weigh the actual literal kilogram in France would weigh 10 kilograms. Essentially, what we are doing when we have that is we are saying, okay, we're gonna just, assume a frictionless object of arbitrary mass, right? It's that sort of thing. We are hand-waving everything, assume that air resistance is not a factor, or assume there's no drag. We are ignoring everything that is inconvenient because it's inconvenient, and we can just make it work anyway. Who's to know? Which, of course, is not always the best way to do physics, but so far it works pretty well, since we actually still do the experiments. Unlike Aristotle! And, yeah, the big numbers and the fact that it's a measurement of mass rather than weight are the things that really keep us from measuring anything in atomic mass units other than just atom mass. Similarly to how we don't measure distances in astronomical units, which is the distance from the Earth to the Sun, because, well, I mean, imagine, saying, oh yeah, the grocery store is just 1/1,000,000th of an astronomical unit away. It's, 1, it doesn't fucking roll off the tongue. 2, it's arbitrarily large numbers. And 3, now you're having to make everyone do math on a daily basis to figure out how far away things actually are. Like, yes, we do that sort of math a lot, like if I say a quarter mile here in the US, or quarter kilometer, half kilometer, whatever, in other places. Fundamentally, yeah, we're still asking people to do math, but it's not, like, huge numbers math. It's... And generally, those numbers have some relation roughly to reality. If we were to just say, yeah, we're throwing out all other systems of measurement in favor of using, these sort of, not necessarily universal constants, but constants instead, that would just throw everything completely off. Especially when things are calibrated in certain ways. I mean, can you imagine, like, being on a treadmill and the display having to read the distance in, a minuscule fraction, essentially? Can you imagine trying to weigh something and, like, any weight at all going into, 10 to the 23rd? It's just, like, it feels farcical. It feels like something someone would come up with for satire. Anyway, that's my more than just 2 cents on what exactly the idiocy of using these numbers for everyday measurement purposes would be. So, with that all said, where does that leave us? Well, like I said, we've got our atomic mass units, we've got our understanding of what protons and neutrons actually are. That means that we can actually start getting into how they work and what they do. But, because this has gone on for pretty long, I'm actually going to call it there for this week. So, thank you very much for watching and or listening, and I will see you all next time.